All right. Hello, everybody. It's funny, I've just been chasing you around the stage. We both just spoke at an amazing UN event for getting more women into tech, and I'm very happy to be here presenting my talk today. And yes, who am I? I'm Katherine. I'm a data scientist, but my background is in computational linguistics, and now I'm working as a conversational AI engineer. It's not only my life, but lucky enough to be my work and my private passion. So please do connect, and you can also find me, online with my tech blogs and with my handbook and things like this, or else hiking in the beautiful Swiss mountains, which is what I've emigrated to. But my topic today, I'm going to cover LLMs as classifiers, why this is a bit of a weird idea, but you might want to try it anyway, or let's face it, you probably are going to. And then I'll use intent detection as a real-world classification use case just to make it a bit more tangible and talk about, on a high level, some possible architectures and techniques you could try, and then I'll try to summarize that, generalizing to other tasks so that you have something you can take home. So firstly, why is LLMs as classifiers a bit of a weird idea? What is classification, first of all? It's a machine learning task, a pretty old one as well, where the model has to classify an input with one of a set of possible labels, dog or cat, happy or so positive or negative in the case of, say, sentiment detection, spam or not spam, which email team should this email be routed to, and so on. Now, large language models, as we all know, these are complex algorithms. They're able to solve a lot of different kinds of tasks, and they usually have diverse and very long-form outputs. Classification, it's usually just one step in a bigger process, and because of that, it often has to be very fast, has to be accurate, has to be consistent, so the same sorts of inputs should get the same label out at the end, and often it needs to be interpretable, exactly for reasons of bias, for example. If something classifies someone as a high risk of reoffense, we need to know why. LLMs are slow, very random, not at all interpretable, and basically LLMs, they want to write bad poetry and plagiarize articles from the New York Times and do anything other than give you one output label, which is what you want in a classification task. So it doesn't necessarily seem like a natural fit, but it might make sense depending on the method that you're using, the architecture. There are certain benefits you might be able to get. For example, for prototyping, I really recommend LLMs because you can very quickly, even for yourself in your private time, if you've got a bit of an idea, it's very easy to scratch your own itch by just trying out the classification task, directly in ChatGPT. They have no training required, not at least to get started, because they have such a wealth of world knowledge from their training data. They have scalability and flexibility when adding new classes. I'll talk more about this later, but in machine learning classification task, each label you want, that's a class, and normally you'd have to add new data and retrain if you want to add a new class, and with an LLMs, it's much, much easier. Another benefit of if you want to turn the prompt into a classification prompt, so basically, if you make your LLM problem a classification problem, then you've got access to things like existing data sets, especially if it is for prototyping. There are classic benchmark data sets online that you would then be able to try out, and all the metrics that are commonly used with this, accuracy, F1 score, precision recall, often these are also easier to compute because the label is either A or it's not A. It's not the label is A and you've got a whole sentence. So if you can turn the problem into a classification problem, you can get access to those best practices. Another benefit is that LLMs can handle diverse and maybe even inconsistent data. For example, if you've got a classification problem that uses customer data, then you've got features in your data that are, filled with information about your customers. But what if you've got a potential customer that you still need to classify? Maybe some of those features are missing, and maybe those features are super useful for the problem, And so in the case of the new potential customer, you just impute that data, so you fill it with some kind of random value or null, but that could affect the performance. And with an LLM, it's much more robust to just taking whatever you want to throw at it. And if you have a multilingual use case like I do, it's easy to build in one language. Easy, famous last words. It's a little bit easier to build in one language and port to another language. So let's look at a real-world use case that I'm taking from my work, and this is intent detection. I just noticed my font is not quite right. Oh, no, it's okay. All right, so intent detection is my big problem that I'm working on at the moment. So I'm working for Swisscom. It's Switzerland's largest telecommunications provider, and we have existing chat and voice bots that customers can contact us with. And right now, with the existing voice bot especially, when a customer calls, the main job we have to do is figure out which team to send this customer to, so a real human to actually handle the use case. And so that requires detecting which product or service the customer is calling about, say internet or mobile, and what do they actually need to get done, what's their problem. And of course, that's a classification task. So our current system has machine learning models and then some rule-based logic and things like this to handle that final target routing. Now, this is a fascinating problem because it's hard, and I like the big, juicy, hard problems. It's hard because of so many reasons. One, there's variability in how customers express themselves, and this can be confusing even for humans. So even when we labeled some data, it can be confusing for the experts to decide what the proper data should be. Yes, somebody's nodding. Somebody does a bit of NLP as well. Another problem, especially in this domain, is that meaning is built up with multiple turns of dialogue. For example, the customer calls, and we greet them and say, tell us in a few words or a sentence what you're calling about, and they just say technical issues. So maybe we disambiguate by looking at which products or services they have and saying, okay, is it about product A, product B, or product C? And they say the first one. That utterance on its own means nothing. You have to have that context. And so that's an implementation challenge, that the meaning comes across multiple turns. Another issue is the context is key, so that's why, as I just said, we want to know what products the customer has and also the status of those. Have they been blocked because of an unpaid bill, for example, or is the internet out in their area anyway? That helps to interpret the intent, because customers are not good at saying what they need, so sometimes it helps to have this world knowledge. Another problem is that customers don't always know what they want or they need. So they might call us wanting to cancel a service, and if they talk to a really great customer service person, that person might realize that actually this person's just maybe financially struggling. They don't want to cancel really, but they just can't afford the level they have, and so they want help with maybe changing their plan. So what sounds like a cancellation call, I want to cancel, that sounds like an obvious intent, but maybe the real intent is a sales call, counterintuitively, but it does happen. And on a similar vein, there's also misalignment between how customers think about their problems and how we're set up to help them. Because we are an organisation that has to figure out, okay, this team of customer agents, what will they be trained in? What sort of tasks will they be trained in? What makes sense together? And this team will have a different set of training. And maybe the way that we've conceptualised that doesn't necessarily align with how customers think about problems. So that can be tricky when you're trying to figure out which is the best team for this customer. Customers can also have multiple intents, which just means you have to try to detect that and then figure out, am I going to have a stack of intents? Will I come back to the first one? So that's a challenge as well. And then, of course, there's noise. There's always noise in the data. In our case, this might be speech transcription errors because, the voice is getting transcribed into text. But, in a more general case, it's any kind of typos, spelling mistakes, hashtags, things like this. Now, I have quite a few little helpful resources throughout this slide deck. Please don't read them and get distracted by them, but feel free to take a photo of the slides. This is an old blog post of mine from when I was first studying this topic about why working with natural languages is hard, so just for a bit of extra information. So look out for those. So anyway, it's so hard, but we do it anyway. And that's because there are benefits to intent-based logic. Firstly, it helps us simplify natural language to make it workable, because as I said, we're never going to be able to capture the variability of the way customers talk to us, but at least within the team, when we're trying to design experiences and things and anticipate problems, it helps us to bucket the kind of things they might be talking about. And this helps us to design so-called happy paths, where we know where the customer might want to flow to get their job done, things like that. Intent-based logic also helps to make our system more deterministic, because instead of just having any kind of output, it's a limited set of outputs, so it's a bit more predictable what's going to come out. It's also more interpretable, because it's the first step in the process, so if we can see what an LLM, say, predicted as the intent, then we can investigate errors and things if things go wrong. And it's also a bit more testable, because, again, you're making it a classification task that has a concrete ground truth label. Is it A or is it B? And then you can test if the model output A or B. This approach can also help to reduce hallucinations, because you can verify a value, is it one of the possible values? Another benefit is, as opposed to having, say, a so-called agent LLM system, which is kind of given free rein to figure out how to solve the problem in whatever way it wants, with a system like that, it might decide, I'm going to make an API call over here, and maybe that's the wrong call with the wrong outputs and things like this. So if you have a more restricted possibility of outputs from the LLM, you can reduce some of those bugs and the latency and costs that come with it. And also, let's not forget that we work in big businesses. We have other teams that maybe need reporting on what's happening in the call centres, and so sometimes it just makes sense from that perspective to have different intents. Again, another one for you to take a photo of. This was me having a little bit of a crisis as I was writing my textbook about why you still need NLP skills in this age of ChatGPT, so enjoy. Now, some of you might be thinking, can't we just use LLMs for this whole process? So if, why not just use an LLM end-to-end? So instead of trying to detect the customer's intent and then do a routing, why don't we just have a giant prompt that says, these are the sorts of tasks that each team can do, and here's the customer utterance. You figure it out. It might work, but there's a few warnings here. So, well, for a start, these are often very, very routine use cases. They don't need the creativity and spontaneity of an LLM. It's just using one for this whole process is maybe going to end up with too much prose and things like this, and not quite getting what you want. So what's, I think, the case for many companies, especially in my sector, is the actual routing logic is pretty good once you know where the customer wants to go. The problem is that knowing part. And so LLMs can be that better front door when, say, the old systems are struggling with their classification accuracy. Another thing is that you might just simply not want to trust an LLM completely freely with your customer contacts, because after all, that's one of your most valuable interactions that you're ever going to have. And then we have the fact that converting an open problem to a closed one and breaking it down into stages, these are anyway classic prompt engineering tips. So we're basically doing prompt engineering by breaking the whole flow down like that. Lastly, nobody needs to panic. We can still use LLMs for other things, so we can still give them a bit more free rein on things like generating RAG answers or answering chit-chat. So yeah, no need to stress there. So now I'll look at some possible techniques and architectures. So these are not necessarily all things that we've tried, but these are things that we've researched that we have in our heads as potential avenues to go. And I've given them all hopefully memorable names. The first one I'm just going to call the classic. And this is the status quo for most companies like mine. So you have a natural language understanding bot, NLU, and it has this machine learning that does the intent detection, and then you've got business logic, maybe some fallback, some disambiguation, things like this to do the final routing. If you really want to use an LLM in this case, if you love spending money and making Sam Altman rich, you could use it for, say, rephrasing utterances and things like that, but there's no LLMs in the classification. So that's the classic. On the positive side, machine learning models, they can be simple, fast, accurate, interpretable, very specific, and evaluation is concrete and can be automated. On the less positive side, as I've mentioned before, if you want to add a new prediction class, you need to get more data, prepare it, label it, retrain the model, and also adding more use cases with business logic is also not very scalable. A real-world example is just many systems that exist today. And, I thought there was a resource on that slide, but there wasn't, so I'm already on the next one. The next architecture I'm calling the hybrid. And this approach still uses a machine learning model for that initial classification, but when the prediction confidence is not very high, you could then defer to an LLM. And the benefit of this is that, all the good stuff I just mentioned about machine learning, you still get, plus you're starting to get the strengths of the LLM. So for those really vague cases that are hard to classify, you're drawing on the huge power of the LLM. But since it's only for those hard cases, you're getting it kind of for cheap because you don't have all of the latency and cost that you would have if you used it for every single interaction. On the less positive side, the system becomes more complex to deploy and maintain. You've got a bigger stack. And of course, LLMs have added complexity, latency, opacity, and are less predictable. And here is the example I was expecting. So Lufthansa Group, there's a nice podcast episode where they're talking about using exactly this architecture. And if anyone's not fast enough with the camera, just talk to me afterwards and I can send these. So the next architecture I'm calling the filter. Again, this is a hybrid approach. But in this one, instead of getting just the top output from the machine learning model and falling back to an LLM if the model's less confident, you just instead get the first, top 10 most likely predictions from the model. So the ones where it's ranking these predictions, it's most likely this or this or this, and then injecting those into a prompt. So then just instead of having every single possibility inside the prompt. Now, this has the benefit of giving you a chance to recover from poor machine learning model accuracy, because in the previous approach, if that top prediction was wrong, but it was confident, you'll never know, and so you'll just have a bad result. So in this case, you are minimizing that risk, same as if you have model drift and the model's not performing so well anymore, you're going to be less a victim to that. But the cons are the same as before, the complexity and costs and things like this. As a real-world example, there is a company called VoiceFlow. They help build chatbots, and they have a couple of nice blog posts about some benchmarking they did on using this approach. So this is the approach that they use. Then we have the fast learner, which is my own name for few-shot prompting, which we're all familiar with. So in this case, you're just giving the bot a bunch of descriptions and examples in your prompt and asking it to make a classification. So you're saying these are the different possible intents. So if a customer calls about tech issues, the label is tech. If they call about admin issues, it's admin. And you can give some examples like, for example, if the customer says, I want to update my address details. And the nice thing is that that's only one example. It's quite specific, but the LLMs are pretty good at realizing, okay, that's just one possible admin issue, but all these other utterances that I'm now getting as inputs, they are also falling into this admin bucket as well. So that's the positive side. So we're using the LLM's out-of-box capabilities, and this has been a real game changer for us. It's very, very scalable to implement newer and better systems. But on the negative side, again, we have all of the issues that LLMs bring, because now you're really just using LLMs with one great big prompt, which can have problems like it's slower to process a big prompt, LLMs can forget the content that's in the middle of the prompt if it gets too long, different things like that. And now we have, what happened there? I see, okay. And then we have the embedder. So with the last approach, the few-shot learner, one problem that we've actually observed is that as you add more use cases, obviously the prompt explodes, and this is causing latency and accuracy problems, but it can lead to lower confidence. So in our system, for example, we try to set it up that for a lot of things, the bot should never ask the customer a question, for example, a specific detail that it needs to execute a task, unless the customer hasn't stated that. But we find that as we implement more use cases, it gets less confident in being able to say, okay, the very first utterance that this customer said actually included all the information I need, and so it asked the customer unnecessary questions. So that's a problem, and so you can end up with just having more fallbacks where it just gives some safe default answer instead of being more specific and confident in its prediction. So an embedding approach, it works a little bit similar to RAG in the sense of the similarity in the embedding. So you've got all of your intent labels and the descriptions that you use in the LLM prompt, but you actually embed those first. And so then at inference time, when the customer has given you an utterance, you retrieve the intent descriptions and labels that are most similar to the customer utterance and inject those into the prompt. And this one helps to tackle some of these problems I keep talking about. It also adds a little bit of interpretability because you understand which intents were actually retrieved. So if the similarity mechanism is what's really failing, you'll see that because you see, of course the LLM was wrong. The top 3 intents that we retrieved were completely wrong because our descriptions were bad. So that can be helpful. But it has the negative side that if the way we write our descriptions is too different from the way customers express themselves, and that's a very real danger, then you might have that problem that you retrieve completely the wrong possible intents, and the LLM has no chance to recover from that. As a real-world example, we have Rasa. So they are another framework for building bots, and they give you the option to turn on this embedding approach if you want. And then we have the tuner. And the thing with this is that, so this is an interesting example that I saw from some Kaggle grandmasters. So as we know, LLMs, they predict the next word. So basically, for every word they predict, it's essentially a classification task. But the labels that it can choose from is just every single word in the vocabulary that it's seen, right? So it's a classification task with a label set of 30,000 or 80,000 or something. And so these Kaggle champions and the resources coming, in fact, I'll just skip to it. These Kaggle champions, what they did is they attached a custom head to a model, and they said it can be even something really simple like gradient boosted tree or something, and they fine-tune it to learn that the probability distribution that it would have output over these, say, 30,000 labels, they fine-tuned that to be mapped to the much smaller label set they're actually working with. So if they only have 10 intents, they're training this custom head to learn to map all the possible words and their probabilities to those 10 labels. And the reason that's useful is they give the example of if the answer could be yes or, positive or pos, right? So maybe the model has seen both versions of that word in its vocabulary, and if you only ever looked for a label output which is called positive, then you might miss all the information that's there in the token pos. And so if you fine-tune this extra head, it can learn to map all the probabilities of pos to the probabilities of positive, which would be one of your labels. And they also said that you can fine-tune the LLM itself as well using some kind of lightweight tuning method. So that's what they did with great results, and I have a couple of resources for that. Now, what we've tried so far, obviously our existing system, which is still running now, is so-called the classic. So it's an NLU-based bot with ML predictions and some rules on top. For now, so our goal right now is to try to completely, overhaul this system, bring it into the current century, make it so much better, and add more use cases and things than we ever could before in a much faster time than we ever could before. So it's also about, scaling up the functionality of this system. And so for now, we found the few-shot inference, so just having examples in our prompt, that's working really well, especially for prototyping, and especially while we don't have too many intents that we need to work with or too many use cases. But we know what's coming ahead. We know that we're going to probably eventually need approaches that reduce the number of possible labels. So we could use this embedding approach where we embed the descriptions and labels and retrieve only the most similar ones to the utterance. And we'd also like to try multimodal models. So this is not one of the architectures I talked about because it's not really a classification approach per se, but we're wondering whether these big models are going to be better able to handle the transcription step than the current system, which uses a separate commercially available speech transcription service. And I have another resource here, again from VoiceFlow, some experiments they did about even simple things like when you're injecting your examples into the flow, should you put please on the end, or should they be capitalized, or what order should they be in, especially if you have an other intent. So that one's also worth a look. But now, how can we generalize this to you guys? Because I assume that you're maybe facing similar problems as well. So the thing is that I talked about intent detection, but these architectures can also obviously be applied to any kind of label classification problem. So my recommendation is to start simple and try it. So first, grab some production data, because probably you've got some because you're not just inventing a new problem for the sake of it, you've got an existing problem you're trying to be better at. So get some data and label it. It really is worth the effort, and especially if you have a team, it doesn't have to take that long. Our labeled data set is only about 1,300 utterances, so with my team it just took us a couple of hours and we had that, and that's been immensely useful for working in an agile way every 2 weeks, running the new version of the bot and testing how it's going with this labeled data set. So it's worth it. Establish your classification baselines. So obviously a simple majority, how big is your biggest class? That's your minimum accuracy you want to be getting. And also how accurate are your existing classifiers. And then I would recommend trying out the few-shot inference approach first. You can do it very simply with a simple for loop and a REST API call if you want to, or even doing it straight in, say, ChatGPT. Depending on which architecture you want to test, then you've got a couple of options. You could either, for the hybrid approach, which is where I said you're only using the LLM for the samples where the existing classifiers are struggling. For that approach, test only the ones that your existing classifiers got wrong, because you should have that in your production data, and then you can combine the results. And obviously, if you want to try the fast learner, then you're just going to test all of them. And then if the results are promising, you can look at some of these other architectures like filtering using confidence scores, or using the embedding approach, or even fine-tuning something. So my tips, though, is firstly, the prompting best practices can be unexpected and model dependent. That's super important if you're going to compare, say, GPT-4 and GPT-4o. So some might be more confident or even more confident in weirdly specific ways. So experiment a lot and make sure in your cross-functional teams you're doing a good job of documenting what's actually working. Include domain experts like conversation designers, or in our case, call center agents, when you're designing the prompts and exploring the model outputs. So the people who are writing the descriptions need to know how the customers talk to you. If you are going to try something in ChatGPT, just make sure that you can put the data in there, so be careful. And remember to situate the problem in a business context. For example, what are the implications of different kinds of misclassifications? If you route a bereavement call to a sales team, that's horrible. So, you have to look not just at your, one number of your accuracy, but look at where the model's going wrong and think about what that means for the business. And also think about whether your data is telling the full story. So we were tempted to look at our production data and whether the customers gave that interaction a thumbs up, like, yes, the issue was solved. But the problem is that customers basically never give that feedback unless they're really angry. So the data is not necessarily always telling the full story. And then also get clever about how to measure your progress, because you're probably working on a problem that has no baseline, no benchmarks. And that's a perfect segue to actually the topic of my last talk at DSC Adria, which was on exactly this topic, and I've written a blog post about that. So with 40 seconds to go, I'm done. Please feel free to get in touch. Thank you very much. And questions?